Okay, let's look at energy changes associated with chemical change, endothermicity and exothermicity. We're going to complete this table by putting a check mark in the appropriate energy change column. If we're looking at a synthesis reaction, that's when energy is released. Decomposition reactions have energy absorbed. Neutralization reactions release a little bit of energy. Combustion reactions tend to release a lot of energy. Now, let's talk about sources of energy. Fuels like natural gas or wood or coal and gasoline provide us with energy, and most is stored as chemical potential energy that is converted into heat. And the amount of energy that's available depends on the position of the subatomic particles that are making up the sample and the composition of the sample. And we use the symbol delta H, or this triangle with this capital H, to symbolize a change in energy that's available as heat. And this is often known as the enthalpy change. And the enthalpy is defined as the potential energy that can be released or absorbed as heat. And there are specific types of enthalpy changes, and these are symbolized by a subscripted explanation. So for instance here, when potassium hydroxide dissolves in water to make potassium ions and hydroxide ions in the solution, this is known as the enthalpy change of the solution, or the delta H of the solution. And you'll notice it has a negative value associated with it. That means heat is released. So this would be exothermic. Here we have the delta H for the combustion of C3H8. This is also exothermic. Here I have solid water, which would be ice, melting to form liquid water. This is the heat of fusion, or the enthalpy of fusion. This is a positive value. So this means it is absorbing heat, and this would be an endothermic process. Let's take a look at the next page. Here, examine each of the following equations listed on the previous page. Consider the sign of the delta H value and determine whether the reactants or products have more stored energy in each case. Put a check mark under the side with more enthalpy. So on the previous page, dissolving potassium hydroxide has a negative delta H value. I pointed that out to you. So it's releasing heat. So that means the reactants had more enthalpy. The combustion of propane, also a negative delta H. So it was releasing heat energy. So the reactants also had more. Melting ice, positive delta H. So it has to absorb some heat energy. So that means the products will end up with more. Replacement of iron by aluminum. On the previous page, that's a negative delta H, so the reactants would have more stored energy. Formation of calcium hydroxide, also a negative delta H, so that means that the reactants also had more stored energy. Let's talk about the energy of chemical bonds. If your textbook has fallen off of your desk onto the floor, when you lift it back up to the desk, you're going to give the text potential energy because of its position above the floor. So potential energy can be thought of as energy of position, and potential energy can be abbreviated PE. And similarly, the electrons in atoms of molecules of any substance have potential energy because of their position. So the negative electrons in an atom relative to the positively charged nucleus and the other nuclei nearby, the electrons have potential energy, and this is called chemical potential energy or bond energy, okay? So chemical potential energy or bond energy, this is stored energy in chemical bonds, okay? So we have the potential energy that has to do with position, and we have the potential energy that has to do with stored energy in bonds. And bond energy is the energy of intramolecular bonds. So intra means within molecules, and those are the bonds that are formed between atoms within a molecule. Now, weaker bonds exist between molecules. These would be known as intramolecular, okay? Or I'm sorry, intermolecular. So intra means within, and then inter means between. Okay, so between molecules, we can have weaker interactions. And the difference between the potential bond energy of reactants and products before and after a chemical or physical change is known as your enthalpy change. And if I'm breaking bonds, that means I'm putting energy in. And then when I'm forming bonds, that means energy is going to be released. So if you're karate chopping a piece of wood, you're putting energy in to break it. The same concept applies when you're breaking a bond. The energy that is used to overcome the electrostatic forces, the positive and the negative forces that bind atoms or ions together, the energy that is used to overcome, that follows that the bond formation is going to be a more stable situation. We're going to end up having energy release. So if more energy is absorbed as bonds break than is released as bonds form, then there would be a net absorption of energy. And this would mean you have a positive delta H value. This is known as an endothermic process, okay? If you take a look at the next page, this is the potential energy diagram for an endothermic reaction. The reactants, potential energy is on the y-axis. Reactants have less potential energy than the products, and the delta H is greater than 0, which means it is positive. So make yourself a note that here, for an endothermic process, the potential energy of the reactants is less than the potential energy of the products. So if you have more energy released as bonds are formed than is absorbed as bonds are broken, you're going to end up having a net release of energy, and there would be a decrease in enthalpy, and this would be an exothermic reaction, which would have a negative delta H value. And this is a potential energy diagram for an exothermic reaction. Here you will notice that your delta H is less than 0, it's negative, and the potential energy of the reactants is greater than the potential energy of the products. That's because you're releasing more. So let's take a look at the quick check here. Complete the right column in the following table by labeling each of the introductory reactions in this section as endothermic or exothermic. The first one is dissolving potassium hydroxide. So that had a negative delta H, so that meant that it was an exothermic process. The combustion of propane, that was also a negative delta H, so that was an exothermic process. Melting ice, that was a positive delta H, so that was an endothermic process. Replacement of iron by aluminum, that was also an exothermic process. Formation of calcium hydroxide, that was a negative delta H, so that was also an exothermic process. And that was all back on a previous page. Let's move on to thermochemical equations versus delta H notation. There are two ways to express the delta H value that is associated with a balanced chemical equation. The first one is known as a thermochemical equation, which includes the energy change as part of the equation. You can see that down here. I have the energy changes within my equation, okay? Now, if you have the energy change being included on the reactant side, that is an endothermic process. So these are both endothermic examples. If you see these energy changes on the products, when they're on the reactant side, it's endothermic. When they're on the product side, it's exothermic. Okay, now, if you have twice as many species reacting, then the magnitude of the enthalpy change should double. You'll notice here that if I have 1 mole of water decomposing here, these coefficients, let me point this out to you. There's a 2 in front of H2O in this reaction. There's a 1 in front of H2O in the bottom reaction. They're both decomposition reactions for water. You'll notice that here, since I have only 1 mole of water reacting, that we took 572 from here, divided it by 2, and that gives you the 286 kilojoules per mole. So the energy requirement was half as much as was represented up here with a coefficient of 2 for you had 2 moles of water decomposing there. If it's an exothermic process, then you will see the magnitude of the heat change appearing on the product side as you have here. So this is for an exothermic reaction. Now, the other way of expressing delta H is with something called delta H notation. That means they will simply say delta H equals at the end of an equation, as they have down here. Here is your delta H equals for each one of these processes. We have the decomposition of water here and the formation of water here. You have a positive delta H in one and a negative delta H in another. Remember, positive is endo, negative, exo. Now, if we go on to the practice problems here. They gave us the delta H values, but they want us to write the balanced thermochemical equation and an equation using delta H notation with whole number coefficients. So here we have the combustion of C2H6. Combustion reactions are where you have oxygen combining with that hydrocarbon to make carbon dioxide and water. Okay, now, we need to pull out the appropriate section here. All right, to balance this, you're going to need a 2, 7, 6, and 4. Actually, transpose that. Put a 4 in front of H2O. No, yeah, 6 in front of H2O and a 4 in front of CO2. Now, let's look at our C2H6. This delta H is kilojoules per 1 mole of C2H6, but I have 2 moles of C2H6. So what does that mean? That means that you need to multiply this value by 2 to give you 2857 kilojoules per mole. okay? So that means that if I'm going to write the thermochemical equation, and this is a negative delta H, which tells me this is an exothermic reaction, that means it would be coming off of the product side like this. You would not make that negative, because anytime you put the delta H into the equation for the thermochemical equation, it is positive, whether it is on the reactant or the product side, and whether it is endothermic or exothermic. Okay, this is simply implying that it is being released as heat. So this is your thermochemical equation here. Now, your delta H notation would simply have the same equation, but we wouldn't include the delta H in the equation. We would write it off to the side here, and this is where you would indicate that it's negative here. Okay? For number 2, we're looking at the decomposition of ammonia. So ammonia decomposes into nitrogen and hydrogen gases, and your coefficient is going to be 2, 1, 3. And if this is kilojoules per 1 mole of NH3, and I have 2 moles of NH3, you need to multiply the 46.1 by 2 to give you 92.2. Since it's a positive delta H, that means that you would include the 92.2 on the reactant side. So this is your thermochemical equation here. If you want the delta H notation, you would write out the equation and just write off to the side. Delta H is 92.2 kilojoules per mole. So there is your delta H notation equation, okay? For number 3, the formation of HBr, so hydrogen combines with bromine to give you HBr. And this is kilojoules per 1 mole of HBr, but I have 2 moles of HBr. So that means you need to multiply 2 times negative 36.1, which is going to be a negative 72.2. So that means for my thermochemical equation here, I need to combine the 72.2 with the other product on the product side. So there's my thermochemical equation. And for my delta H notation, I would write delta H equals negative 72.2 kilojoules per mole off to the side of that second equation.